Okay, let's start using what we learned so far and add a little bit on top by starting with a bigger project, and that is a fountain. So I have a couple of references pictures here. We will of course not, match this perfectly, especially since water you would usually simulate with Flip and all that. This is more, again, a concept example, trying to explain concepts and ideas and workflows. So what we will start with, just out of practice, is the actual fountain base. So we would probably do this with a tube. In Houdini 19, this already creates it as a polygon. Let's use Tommy so that we have a good idea about the size of the whole setup. So let's make this to something that makes sense. Then we can start poly extruding this out before we move it to the ground. So a simple poly extrude should work here. Be careful, keep in mind that the inner face is not created by default, so we have to turn this on. And now the cool thing is that we want to extrude the top side, and since we're in Houdini, we want to do this procedurally. So how can we find this? We can use the automatic side group that comes out of it, and we can use this in another poly extrude to then extrude this up. I mean, of course, you can also use groups to find the top part and all that. It's not the only technique, but it's just one technique I wanted to show you. And now you can see only the side edges will be extruded. And from that, we can again create a side group, which will overwrite the old one. And then we can do the same thing again. Actually, we could even copy that one, but let's do it one by one. Because by using this side group, which now came out of the second poly extrude, we can extrude this to the edges. Well, actually, no, it did not override it. Now we have both in one. So we can fix this by just deleting the group that came, or actually, there are multiple ways. We could use a group delete to delete the group that came out of the first poly extrude, or we're just careful of just naming this differently. We call this extrude side 2, which is, just to be clear, this side part here, because that's the side of that extrusion. And then we use that instead of the first one, and then it looks like this. No, it will not win any kind of architecture prizes, but it's just, a nice little practice to create something like that. And then maybe, let's add a poly bevel on top, because this is interesting for rounded stuff, because by default it creates those bevels also on the flat areas, and we only want them on the edges. So we can turn on the exclusions part where it says ignore flat edges, and then we just dial to the point where it doesn't happen anymore, and then we're golden. So, and then finish this maybe by just putting this on the ground. And of course for this we can use a match size, and we set the justify wide to minimum and leave the rest at the default. And now we have a good base for our fountain. Unfortunately, we started to become pretty big. So as you can see, our little Tommy here is disappearing. So let's lower this, or we could use a transform at the end. Different ways of doing this, but I think I stick with the source. So maybe something like that. And then we merge this with the grid, of course, and we can get rid of Tommy now, or maybe move him to the side, something like that. Now to the interesting part. We want the fountain points to come from kind of a circular source. So we need some source areas or some sources that are, aligned in a circle. There are multiple ways of doing this. So for example, since we so far used a sphere as a source, we could use a sphere, and then maybe we could use a copy and transform to rotate it around the center, very similar to our staircase example. And for this, we just move a sphere to the side, and then one copy of it, we move a little bit, or we rotate a little bit, and then we can create multiple copies of that. To be very exact, we could actually say, okay, how much does this rotation has to be to really have an even distribution? We can just say, okay, we need 360 degrees divided by this number here. So we could just see what the name of the parameter is, which is NCY. Don't ask me why. And we can do this by hand with the channel expression NCY, and this will work. Or if that's too much work for you, just right click, copy parameter, and then you could have just pasted that in your expression here with a relative reference. Comes out the same. And that this works, you can see here, because now the number is changing and with it the rotation amount or the degree. And as you can see here, this creates an even circle. That's just, one way of doing this. Another way, which obviously would be much simpler, is just a circle. Just create a circle and change the plane to this maybe. And then you can scale that thing. And the cool thing is it has points as a source and we can change the divisions just like that. Very straightforward, but both is a viable option. I take this circle, it's much simpler because in this case I want to take the points as our source. Let's make a few of them, maybe this. And if I show my, oh, that's actually not too bad. If I show my fountain base here, let's make this a bit smaller, maybe to something like that. Okay, now we use that as our source for the PopNet to save some time. We don't need to create everything from scratch. And now when I start this, of course, the points are created on the surface of my circle here. And this, of course, is how we know it, because that's what the pop source does by default. It scatters onto the surface of the first input. Now, let's change this. And we can do this by changing the emission type. And I'm always getting confused which one it is. There's all points and points. Let's try all points first. And to check if it's the right one, I always go to birth. And as you can see here, all the birth rate options are grayed out. And that is because it currently will, let's rewind this, it will only use the points that come from the geometry. So let's press start and see what happens. Well, they don't do anything because they are emitted on the same position and then they stay there because there is no force. So let's add the basic gravity force. And now we can see they come out of this in a very, even way. Let's turn on real time at least. We can switch this to points because now we can say, okay, from those points, we want more points to be emitted every subframe than just those, what is it, 10 or something, 8, 9. So if I rewind now and have switched this to points, then, well, it doesn't look that much different because all those points still come out from the same position, but we can now play around with the attributes. So let's create this kind of, spray upwards thing. And we can do this, of course, by changing the attributes to set initial velocity. And since it's supposed to be upwards, let's try, I don't know, 3 in Y. And the variance, of course, creates the spread. So let's leave that. Why not? And then let's start and see what happens. Okay, that's promising. Let's make it stronger, of course. So 8 maybe. That's not too bad. And you can see, okay, that looks pretty, fountain spray-y. Maybe the spread is a little bit too strong, so maybe let's lower this to 0.4 or something. And now we have less spray. That's not too bad. Let's quickly test what would have happened if we have used all points, because now you could have seen it's very few points because it's just the points that are already there and we can't change the amount. And this is why we chose points so that we can set the constant birth rate per second. And then you can see we can change the density of those points, of course, or the amount. And now you can see it looks pretty much like a fountain. But there is a problem. They are not pointing towards the center. I mean, first of all, they go on forever. So let's switch this first, maybe to 3, let's say. Yeah, and then a life variance of 1. That's not too bad, I think. Let's leave it at that. I think that's good enough. So how can we make sure that those streams are pointing towards the center? Let's see what we can do here with the attributes. I mean, we can change the direction. I don't know, let's try something like that. And here you can see, sure, we can change the direction, but how can we change the direction for every single point separately? Well, it's actually not possible. You can't do that with a pop source. We have to find another way. And the other way is just set the velocities at the start outside. So basically we bring in a velocity on the points that we emit from, and the PopNet will actually inherit that. And this is why by default it's set to use inherited velocity, and this is set to 1 because that's what it's doing by default. It's just that so far we've never had velocities on our source geometry. So how can we do this? Well, let's try to set this, and we can use, of course, attribute create, because velocity is just the attribute v, as we've seen, and we can set the same attribute. Not only we cannot just read it out, which comes out of the PopNet, we can also set it beforehand. So let's create a v attribute on the points. This will be a vector, as we've seen. So let's just, type something in, maybe 2 in X and 2 in Z, something like that. And you can kind of already see that it's working, because now we have this. Looks a bit strange, but it is actually what we want. And that is because I was a bit sneaky. I switched it back to use inherited velocity. So currently it ignores our velocity that we set here and uses directly the velocity we had. Now let's bring this back to what we had before, which of course wasn't too crazy. It was just, I think it was 0, 8, 0, so upwards. But then we have another problem, and that is, it's a perfect upwards. It doesn't have a variance. Now, actually, you could add the variance yourself by using an attribute randomize, but you will run into a couple of problems, because remember, those are only the starting points, not the points that are emitted later on. So it will be tricky to create this kind of variance for every point that is emitted. But technically you could add to the current velocity with add value a random direction like this for the v attribute, of course. And then you get a bit more variation, and it looks like this. And here's the problem. This will only work per point. So we will not do this, because we can actually mix the two techniques we've seen. We can set a starting velocity, and on top we can actually, and this is why it's the second option is there, add to the inherited velocity, and then we can use our variance here again for every point that is emitted. So combining the two techniques gives us the best of both worlds, and now we have the variance again, but the main upwards movement, as you can see here, doesn't come from the PopNet. It comes from the outside main velocity that is already on the points, as you can see here. Why did we do all this again? Because now we're back at 0. Well, the reason is that we can now change the main direction, not the variance, but the main direction for every point separately. But the trick now is, and this is why I actually wouldn't use the attribute create for this, I would use, as usual, vex for this, because it's so much more handy. Because I can do something really cool, and that is I can set the velocity to the current position. And this will result in the following. You can see currently they move outwards from the center. If I say negative p, they go inwards. There you go. And if I add to this, and this is important, we want to add to this an upwards movement, which we can create with a set function, then we just use the 0, 8, 0 that we saw before. So we point in the direction of the position, whatever that means, and then we add an upwards velocity on top, and then it looks like this. So why the hell does that work? Why does setting the velocity to the position result in this kind of direction? Let me explain this to you, because that's a really cool trick. Because it is actually a property of positions or vectors in general. Because when we look in 2D and see this point here at the 2D position 4 in X and 5 in Y, then the interesting thing is, and you know that, is that this is not just a position 4, 5, but also a vector 4, 5. And since this number is relative to the center of our coordinate system, a position is always also a direction, which is really strange, but a great phenomenon that we can use to our advantage. And we will actually use that a couple of times throughout the course. So the position of a point is always also the direction towards or away from the center of its coordinate system. That's just the nature of it. You don't have to come up with that yourself, just accept that it is like that and use it to your advantage. And if I use this in 3D space, it's basically the same. We have 2 points here and both have a certain position for X, Y, and Z. And when we kind of draw those as a vector, surprise, this is a vector from or towards the center of the coordinate system. It doesn't matter if it's 2D or 3D, that's always true. And this is what we use in Houdini here. because if we look at actually just those points here, and this is the center of the world right there, and we can quickly comment out this part here. And by the way, I can make this bigger. This is possible in Houdini 19 with Control plus. So if I comment out the upwards movement part, then what is left is this. The velocity equals the position, and we can actually visualize this when we visualize the velocity. And let's just make it a bit longer by pressing D under Visualize, no guides. Here it is, Scale Vectors, and here you can see now they get longer. Those velocities, when we just set them to the position, are just pointing towards the center, or away from the center actually. And to turn this around, I add a negative to this, whoop, and now they just change their direction towards the center. So keep that in mind. It's just a very simple and super useful trick to point towards the zero of the world. And again, now we can add to this the 080 on top, so that they not only look towards the center, but also upwards of the center, so somewhere here. And this is exactly now the idea, that we have this velocity that goes inwards to an extent, but also upwards. When we combine this with the variance from the PopNet, then we have everything we want. And maybe we want it less strong towards the center. What we can do here, for example, we could just multiply this with 0.5, and then it will be less strong. Let's rewind. There you go. Now it's a bit less strong towards the center. And now we have our first part of our fountain. Now let's add the center part to it. So if you look at the reference again, there's usually one big one in the center. Let's do this as well. And just keep in mind that you can just use an at, for example, to just create a single point. And in this case, that's exactly where it should be, at 0. And by the way, we always work here relative to the center of the world. And that's usually something I would recommend when working in effects. You always work in the center of the world, because everything all of a sudden becomes much easier. And this is what I try to do even for complex scenes. Sometimes I even move the scene to the center so that I can do that, and then I just move it back. So anyway, I can now merge this point and the circle, and on purpose I left the point wrangle out here that sets the velocity for the circle. And for the add, let's actually set our own velocity. So let's set this to also an upwards vector, so 0 something 0, and this time we make it stronger upwards. So this way we can have a different main velocity for this point than for the circle, and this will result in this, that we can control the strength separately. Actually, we went a bit too far, maybe 10, and here you can see the idea behind that. Yeah, pretty cool. And if we merge this together now with our base here, we are getting pretty close already. There you go. Only problem is we have black water. Let's fix that. Now, of course, what we could do is we can just drop a color node here, and all of a sudden it becomes white, which is actually maybe exactly what we want. And then we run this, and it's not too bad, but it's kind of boring. It's not really there. And the reason is that actually, and I have to be careful now, water doesn't have a color, but water has a perception of color based on its properties. Generally, the first thing is water seems to be bluish because it reflects the environment. So by itself, it's not blue, very important. It is a reflection. But for this simple example, we could start with a bluish color. And also, when you look at it, you might say, okay, it also has a whitish element to it. And this is usually literally the white water. So what's happening there is that the particles are breaking up, and they become so small that they break the light so much that you get a diffuse reflection. And this results in a white perception of the water. This is why it's called white water. And there are many ways of kind of simulating this, but we will do a simple way of doing it. We just take the speed of things. So the idea here is, and again, this is really just to explain concepts, we use the property of a point, its speed, to colorize the water. And this is something we can do with the color as well, because we can use a ramp from attribute. So we would say, okay, if the speed is low, it's bluish, and if it's fast, it's whitish. And in between, it changes its color. Sounds good. So what we need here is the speed, and we have the speed already, right, in V. So let's try that. That didn't work. I mean, it's cool, something is happening, but now we have kind of a rainbow fountain, which is cool, but not what we wanted. What is happening here? Now, the problem here is that since v is a vector, now careful, don't get mixed up. It's called v because it's a velocity, not because it's a vector. It just happens to be that a velocity has a direction and therefore it's a vector. And what's happening here is that x, y, and z of v are now colorized differently. So they use this ramp. So the red channel uses this ramp, funnily enough. The green channel and the blue channel all use this ramp separately. And this is why the colors are mixed based basically on the direction. In other words, you can't use vectors in a color ramp, unfortunately. We have to use a float, and the float would be not the direction of the velocity, but the amount of the velocity or the speed. How do we calculate this? We can actually do two things. We can either do this by hand, and this is what I prefer because it explains better what's actually happening. Let's create our own attribute here called speed, and this is basically the length or the magnitude of the velocity vector. So length is a function that you can use, and careful, don't use len. This also exists. Len gives you the amount of elements. So for a vector that would always be 3, no matter what. But length is the actually length of the vector, so the speed of the vector, and this will then be saved in speed. And this boils down to one super cool another thing about vectors, and that is that they have 3 elements, but they technically save 4 information. Because when we look at a vector again, and this time, I use 3 elements because let's say this is 3D space and we ignore z, so this is a vector of 2, 2, 0. And then we have another vector, 5, 5, 0. Then when you look at the vector, you can see it's actually the same direction. So in terms of direction, there's absolutely no difference between the two. But of course, what is different is the length. And that shows you that in those 3 numbers, x, y, and z, basically is a 4th number involved, and that is the length of that vector. And this is pretty cool because basically with 3 numbers, we can save 4 informations. And this is what we're doing here. We are reading out this 4th information, the length of the vector or the speed of the vector, and then save it in its own attribute. Why would we do this? And actually let's call this speed, so that we can use the color and then type in here speed, which is now a float, and it actually works. It's just that our range is wrong. So let's quickly look what comes out of this. Because speed is in meter per second, it actually can go quite high here. And I had no idea what the range is. So it is something between 0 and 20. Let's try 20. And actually this is usually too high if you go the full maximum. So let's maybe choose half of that. And maybe even 5 and something like that. So here we have actually, interesting enough, the opposite thing. We have that, let's try 7, I think. Then it actually will be white at the top. So since the gravity is slowing it down, in this case, the slower points I want to be white and the faster points I want to be blue. So something like that. So I know this doesn't necessarily make sense, this logic with the speed, but my point here is that we can use speed as one possible attribute to read out the color. Now, in the interest of not hiding important notes from you, you could have done this a bit easier maybe with the point velocity node. So a lot of people use that actually instead of calculating the speed themselves, but I still find it very important at least to understand what speed actually is here. So the point velocity node usually calculates velocity. We will talk about this in another video. We can turn this off. So let's just switch this to keep incoming. And then up here, you might have seen it, there is a checkbox called calculate speed. And this now gives us a new attribute called surprise speed. And this should give us the exact same result if we good. And there you have it, it's the exact same result. So some people might use the point velocity instead of calculating the speed themselves. It's up to you, whatever you want to use. But I think understanding the calculation is still important. Another thing that we've already seen is we could have also used the age. So let's try that. We, by hand, create our own age, a normalized age. And as we remember, we did this by making sure we're not using nh, but something different. And then we just take the age and divide it by the life. And then we have the age, and we can use this as well if we want. So there are many ways of doing this. Maybe, yeah, something like this. And now it would be the complete opposite. So it's up to you really on your case what makes the most sense for you. And one last thing so that we can finally finish this video, we could now add a little bit more, the impression of motion blur. So usually when you look at a fountain, it doesn't look like this. It doesn't look like, small dots flying around. You would more perceive it as streaks. And this comes from the motion blur or your kind of laziness of your eye. This is something in rendering that you will then actually be able to turn on. But just, to visualize it or also to use it for certain effects, you can also turn this into those liney looks. And for this, you can use the trail node. Now, I will just quickly show you how to do this. We will talk about this in a separate video very soon. So you can switch this to preserve original, then maybe increase the trail length to the length you want, maybe 3, and then you use an add node that creates curves out of this. So you go to polygons, by group, and switch here to by attribute and use an attribute we've already seen, and that is ID. And then you have those lines here, and it looks a little bit more like a fountain, how we would perceive it. So again, I know this was a bit fast, but I decided not to make this video even longer by explaining all this properly. If that interests you, you can see there's a trail video where we talk about this in depth. And now we have something where we can say this looks a little bit like a fountain. So as you've seen, there are many different techniques that we used here. A lot of them we will reuse later on. So you learned a lot of important stuff. One of our biggest projects so far, I think. So I hope this is helpful. Thanks very much and see you later. Cheers.